Let's look at two examples where we compute the variance of a variable. In this first example, we'll look at a discrete variable. In this case, x only takes on the values 0, 1, 2, and 3. What do we know? Well, we know that the expectation of x is 4 over 5. And we also know that px of 0 is 9 over 20, and px of 1 is 7 over 20. Of course, this px is the probability mass function of x. So it's the probability, for example, that x is equal to 0. Okay, the question that we want to solve is, what is the variance of x? Now, you probably recall that the variance can be computed with the following formula. The variance of x equals the expectation of x squared minus the expectation of x squared. Now we already know what the expectation of x is equal to, but we don't know what the expectation of x squared is. In order to find that expectation, we first need to know the entire probability mass function of x. We already know that px of 0 is 9 over 20. Px of 1 is 7 over 20. These other two values, px of 2 and px of 3, we still need to find. So, well, let's call them x and y. How can we find x and y? Well, first of all, the sum of all these probabilities in this table has to be equal to 1. And the total probability is equal to 1. So that means that, first of all, 9 over 20 plus 7 over 20 plus x plus y is equal to 1. We also know that the expectation of x is 4 over 5. Now, in this case, for this variable, the expectation of x is 0 times 9 over 20 plus 1 times 7 over 20 plus 2 times x plus 3 times y. And this should be equal to 4 over 5. What you see here on the left-hand side of the equation is simply the definition of the expectation of a discrete variable. So you see that we end up with a system of equations, two equations and two variables. So that is something that we can solve. And in fact, if you rewrite these two equations, you will find that the first equation tells us that x plus y equals 4 over 20. And the second equation, if we rewrite all the fractions as a fraction with a denominator 20, then we find that 2x plus 3y equals 9 over 20. Well, it's a very simple system of equations, two variables, and if you would solve that, then you would find that x is equal to 3 over 20 and y is equal to 1 over 20. So now we have the entire probability mass function of x. Okay, how can we compute e of x squared? Because that's what we still need to compute the variance. Well, the formula is very similar to the formula for the expectation. So we take on all the values that x can attain, take their square, and multiply them with the corresponding probability. And so in this case, we get 0 squared times 9 over 20 plus 1 squared times 7 over 20 plus 2 squared times 3 over 20, and finally plus 3 squared times 1 over 20. Now, if you would compute this entire expression, then you would find 14 over 10. Well, and that's it actually, yeah? Because now we have everything we need to compute the variance. We can use the green formula that you see on top of the screen, and there we see that the variance of x is now equal to the expectation of x squared, 14 over 10, minus the expectation of x squared. And let's take a look, what was the expectation of x? Well, you see it right here. It was 4 over 5. And it gives us a variance of 38 over 50. Let's take a look at the second example. Only in this case, x is a continuous variable, and we know what its cumulative distribution function is. And it's a function that you see here on the screen. So if x is less than 0, then this function f is 0. For x is between 0 and 1, it's x to the power 3 plus 3 times x over 4. And for x is larger than 1, it's equal to 1. And so this is basically a continuous variable that only takes on values between 0 and 1. The formula for the variance of x, the one that we're going to use, is still the same. It's still the expectation of x squared minus the expectation of x squared. So we need to compute these two expectations. And, well, the cumulative distribution function is not the right function to do that. We need the probability density function, so small f. Maybe you know that the probability density function of a variable is actually the derivative of the cumulative distribution function. So we're going to derive our cumulative distribution function to obtain the density function. So let's see what we get. So our density function, let's split it in 3 parts. X smaller than 0, x between 0 and 1, and x larger than 1. First part, for x's smaller than 0, our cumulative distribution is equal to 0. The derivative of 0 is 0, so we get 0. Same thing happens here. Here our cumulative distribution function is the constant function 1. For all x's larger than 1, the derivative of a constant is 0, so here too we get 0. Then the middle part, well, here we actually have to compute a derivative. X to the power t plus 3 times x gives us, of course, 3 times x squared plus 3 over 4. And so this is the distribution function, the density function that we need. The expectation of x for a continuous variable is given by this formula. So we need to use an integral, and this gives us the expectation of x. Now in this case, our continuous variable only takes on values between 0 and 1. So the density function is 0 for all x's smaller than 0 and all x's larger than 1. So in this formula, we can integrate from 0 to 1 instead of using the boundaries minus infinity and plus infinity. Now we can plug in the density function that we just found, 3 times x squared plus 3 over 4. So we get this, and this is of course a very simple integral. It's just a polynomial. You can take the 1 over 4, put it in front of the integral, and then compute this, this integral of this polynomial. If you do that, you will find 9 over 16. Okay, for the variance, we also need the expectation of x squared. And actually, the formula that we're going to use to compute the expectation of x squared is very similar to the one that we just used to compute the expectation of x. It's actually the same formula, but instead of multiplying the density function with x, we're going to multiply with x squared. And so we get this. Well, here too, we can integrate from 0 to 1 instead of using the boundaries minus infinity and plus infinity, because, like I already said, for all x's smaller than 0 and all x's larger than 1, our density function is 0. So that doesn't really contribute to the integral. If you would compute this integral, again a very simple integral, just a polynomial, you would find 2 over 5. Well, now we have everything to compute the variance of x, because the variance of x was equal to e of x squared. Well, we just found out that that is equal to 2 over 5, minus the square of the expectation, 9 over 16. Well, if you would compute this, you would find a variance of 107 over 1280, or 0.0836.